anggota Sivitas Akademika UI yang terbaru ini akan juga sama turut berkontribusi dan menyumbang bagi masyarakat, kesejahteraan masyarakat Indonesia, integrasi nasional, integrasi sosial, tanpa paksaan, tanpa kekerasan. Itulah tugas kita bersama. Semoga dengan bergabungnya Anda semua sebagai mahasiswa baru UI, Anda akan semakin bersemangat untuk berkontribusi. Bukan hanya di aspek akademik saja, tapi juga di aspek pengabdian pada masyarakat. Selamat datang di kampus UI. Terima kasih.
Kita bertepuk tangan secara virtual ya. Selamat datang di kampus UI gitu ya Sasti ya.
Baik, kami ucapkan terima kasih kepada Dr. F. Eriseda, Kepala Departemen Sosiologi, yang tadi telah menjelaskan tentang integrasi nasional dan integrasi sosial.
Betul sekali, nanti kita akan masih mengikuti talk show berikutnya dengan narasumber Bapak Ahmad Gamal dan juga Dr. Ima Mayasari. Namun jangan kemana-mana, tetaplah bersama kami dalam KAMABA UI 2021, Satu Karena Beda.
That was really a slowdown.
Okay. Yeah, I think last week we saw in the TV that people in London, I think they were watching football. I think nobody wear mask. I think incredible.
Well, you have the Olympics now, you know.
Yeah. I don't know. Do you think there might be rising new cases in the next or 2 weeks from now in England?
Baik, masih dalam kegiatan KAMABA UI 2021, Satu Karena Beda. Sasti, sebelum nanti kita melanjutkan sesi talk show, kali ini kita akan mengikuti sesi masterclass. Ada siapa nih Sasti ya?
Ya, masterclass topik ini kita terhormat sekali karena mendapatkan sharing pengalaman dari kalangan industri dan profesional. Dan kali ini dalam masterclass ini akan diisi oleh Profesor Gerard Amoro, pemenang Nobel Laureate Fisika. Dan pada sesi ini, Reska akan dipandu oleh Bapak Asta Ekadianto, Direktur Center for Independent Learning Universitas Indonesia. Untuk itu, langsung saja kami serahkan kepada Bapak Asta Ekadianto.
Baik, terima kasih. Good morning, Professor Muru. Are you hearing me now?
Good morning. Good morning, everybody.
Yeah. Prof. Muru, could you step a little bit back because your face is a little bit chopped and, that's better. Very good.
Is better now?
Yes,
Okay.
yes, better. Thank you very much.
Thank you. Yeah.
Okay, so thank you for giving us the chance to listen to your lecture because it is very interesting. Many of our, not only students, of course, our professors, even you have chat with our rector just now. We are keen to hear about your experience, about your knowledge, especially, of course, the motivation behind everything. Because I've read your biography, a short biography, and I think it's quite very, very interesting in the way that you are consistently focusing on this area. So many people have influenced you, and of course, I think you have influenced a lot of people. So I would like to probably
Recording
first,
in
of course, you have
progress.
met our rector, but I would like officially to introduce you to our rector, Professor Ari Kunchoro. He is now also in the Zoom meeting, and also many of our head of university, vice rectors, academic affairs, Professor Abdul Haris, vice rector of finance and logistics, Mrs. Vita Silvira, secretary of the university, Dr. Agustin Kusmayati, and also vice rector of human resource and assets, Professor Dedi Priyadi, DA, which also graduates from France, by the way. So there are also lots of guests now attending the Zoom sessions. We have many researchers, academicians also from not only Universitas Indonesia, but also from many other, let's say, research institutions, partner universities surrounding all around Indonesia. So we are all keen to hear from you. And also our students, there are about 8,000 students now watching you from YouTube. These are new students and also others which are also our old students, or let's say more senior students who are also, some of them are attending also in this Zoom meeting. So there are lots of people that are going keen to hear from you. And probably at first I would like to introduce Prof. Ari Kunchoro, if you want to have some welcoming or let's say hello to Professor Muru, please, you may do so.
Hi, Professor Moro. Welcome to University of Indonesia. It is a little bit unfortunate that we cannot have on-site event, but I think we have to accept that this is modern era. Yes, it is the time for us to use technology. So again, I'd like to thank Professor Moro for delivering a general lecture to our student. It is my honor as a rector and also our honor as a University of Indonesia. So again, welcome to Professor Gerard Moro. I think we have been listening to your lecture. Thank you very much.
Thank you. Thank you very much. And I would like also to really also to thank you very much, Professor Ari Kunchoro, for these invitations. In spite of the fact that, you know, it's in the middle of my holiday vacancies, you know, I'm vacationing in the south of France, but that it's a pleasure to be with you and to deliver this lecture on one thing which is very, very dear to me. It's about light and extreme light. Okay.
Okay. Thank you, Professor Ari Kunchoro. Thank you, Professor Muru. Maybe we will start immediately with the lecture. And before that, I would like to present and also read a little bit about Professor Muru, so that we know, or everybody might know about him, but probably I would just have to, of course, introduce officially. Allow me to introduce you, Professor Muru. So, Professor Gerard Muru is professor, member of Haute College of École Polytechnique, A.D. Moore, Professor Emeritus at the University of Michigan, Ann Arbor, Michigan, and the director of the new center, IZEST, or International Center for Zeptosecond Exaward Science and Technology at École Polytechnique. Mr. Gerard Mou was born in Albertville, France. He studied physics at the University of Grenoble, and then at the University Pierre et Marie Curie in Paris, where he earned his PhD in 1973. He later moved to the United States and became professor at the University of Rochester, where he did his Nobel Prize awarded work along with Donna Strickland. He subsequently worked at the University of Michigan and then École Polytechnique in Paris. He's recognized worldwide for his work in ultra-fast science and technology, mainly for his co-invention with his student Donna Strickland of the laser amplification technique called chip pulse amplification, or CPA. In 1985, Strickland and Muru succeeded in creating ultra-short high-intensity laser pulses without destroying the amplifying material. First, they stretched the laser pulses in time to reduce their peak power, and then amplify them, and then finally compress them. The intensity of the pulse then increases dramatically. Chip pulse amplification has many uses, including femto-ophthalmology for corrected eye surgery, especially for cornea and cataracts. The CPA has been the gateway to attosecond field and high field physics. As such, he is often revered as the father of ultra-high field science. He returned to France in 2005, proposed the creation of the European infrastructure, ELI, or Extreme Light Infrastructure, and he was the coordinator of its preparatory phases. It is a 1 billion euro facility, ELI, is built on 3 countries, the Czech Republic, Romania, and Hungary. It's dedicated to the production of extremely intense pulses as a novel paradigm to high-energy particle physics. Gerard Muru is a member of National Academy of Engineering USA. He is also a foreign member of the Russia Academy of Sciences, Austria, and Lombardy. So please welcome Professor Muru for the lecture. The time is yours, Professor.
Okay, I have to share my screen, I guess, now. I'm sorry, I'm trying to share my screen with you.
Yes.
I don't understand what's going on.
Or we could share it for you.
Yeah, okay, it's
Yeah?
fine. Yeah, good.
Good. So,
If you
okay.
can.
Yes, we can. So you can just say continue or. So now it's shown, Professor.
Is that, it's okay for you now?
It's okay?
Okay.
Yes.
So do you see, is it, I mean, you see the full screen where you are? Hello?
Can we?
Can you hear me?
Yes.
Okay, so I can go.
Yes, you can
Right?
go.
Okay, so thank you very much for these invitations, and to be, I'm very glad this way to be acquainted in a sort to this really nice university and prestigious university of University of Indonesia, okay? Thank you very much. You changed my screen, and this is good. Okay, so as I say, really very, very pleased to be here, in spite of the fact that, you know, I am right now vacationing in the south part of France, in what we call Provence. So let me tell you my passion for extreme light, okay? And I'm really pleased to also introduce my graduate student, Donna Strickland, who shared the prize with me, okay? And when the Nobel committee called me, you know, on the Tuesday, the first, you know, but the Nobel Prize for Physics is always on the Tuesday, the first Tuesday of October, okay? And so when I got the call, of course, I was really extremely pleased, not only for me to get the Nobel Prize, but also I was doubly pleased because of Donna Strickland, my student, you know, got the prize. And I have to say one thing about that, because Donna is a third woman, you know, behind Marie Curie and Maya Gopper-Mayer to get the prize, okay? So it was an extreme honor for me, you know, her advisor to have also advised a Nobel Prize winner. That was very, very nice. Okay, so I'm going to talk to you about light, okay? Can you switch light, please? Can you switch? Yes. I'm going to talk, no, come back. Yeah, thank you. So I'm going to talk about light, and of course this is, I'm starting, you know, from the very beginning with just a light bulb, okay? And the light bulb, in fact, generates incoherent light. And, you know, I mean, all the photons which are really emitted by this bulb, light bulb, you know, are incoherent. You know, they have no relationship between each other, and they go in all kinds of directions. Now, next slide. Now, this is a laser, okay, of course, and you see the laser is what we call a coherent light, and I will say a few words about this, but you see that now the light is going mainly in one direction, and plus is made of a kind of unique kind of photons, okay, not as, and they are going all in the same directions. So next slide. So the light from a laser can be emitted, can be continuous, or as I will show you, also can be also emitted in bursts of light, sometimes very short bursts of light. Next slide. Yeah, the bursts can be extremely short, and this is the one I'm going to talk about mainly. They go in, they are measured in femtosecond. Femtosecond is a billionth of a millionth of a second, okay? It's 10 minus 15 seconds, billionth of a millionth of a second, okay? So this is extremely short, and you will understand why sometimes we need to do that. Next slide. Yeah, so now I'm coming back to the light, okay? I talked about incoherent light, okay? And incoherent light is very much like a bunch of marathon runners, you know? And you see marathon runners, they go in one direction, roughly, okay? But they they are all dressed differently. They don't know each other. They have no relationship with each other. And they, of course, go at different speed, different pace, okay? Next slide. On the other hand, a coherent light is very much like an army marching, okay? Where now all the soldiers, are wearing the same uniform strictly. They go strictly at the same pace, okay? And if you know the position of one soldier, you will know the position of everyone, okay? And this is very much like a coherent light, okay? So next slide. So this is Ted Mayman, okay? He is really the inventor. Inventor is really Charles Townes, but Ted Mayman was the first one really to make a laser work, okay? In 1960, in fact, it was May 1960, okay? Then Mayman made the first light with his laser, and you see the laser in his hands. At that time, it was very rudimentary, okay? And so now, what is amazing about these lasers? If you take one laser, okay, you can almost, you can do so many things, okay? And you would understand why. Okay, next slide. So if, for instance, if you're taking a laser, I can have this laser slow down atoms to almost rest, okay? And so that means, next slide. So that means that when you are slowing down atoms, we physicists, we say we are cooling atoms, okay? Because the temperature is, of course, an expression of the motion of the atoms. So we can really slow down atoms, that is, we can cool now atoms to very, very low temperature, and there is a huge amount of really applications now where you really need extremely controlled cold atoms, okay? In metrology, there's a number of applications. So this is the thing. One thing you can do with laser, you can slow down atoms, cool atoms. But what you can do also, you can almost do the opposite, okay? Next slide. Yeah, you can accelerate particles to almost the speed of light, okay? This is very important. So you see, you can really do this two very different things. So you can accelerate particles. So next slide. So the particle gets energy in a giga, very high energy range, like many giga electron volt, and soon I hope we will get the TeV, tera electron volt. So you see that with the same photons from a lasers, you can basically produce events with almost 30 or 25 orders of magnitude, okay, in terms of energy. So this can explain, you know, why we can really do so many things with lasers, okay? By the way, here with the high intensity laser, with very short pulse lasers, we are in a situation where we are going to accelerate particles, right? And we are going to accelerate particles to the relativistic regimes, okay? The particle will go at very close to the speed of light. And so the applications will be in accelerator physics, in nuclear physics, cosmology, non-linear QED, general relativity, and you name it, large number of applications. And of course, this is what I'm going to talk about, okay? Mostly about high energy that are produced by the lasers, okay? And this is the reason why I got the Nobel Prize. We got the Nobel Prize with Donna. Next slide. Okay, now, why do we want to have very, very short pulses? Well, we can, if we want really to get very high power, then, you know, if you have a very short pulse, it's very easy to get very high power, okay? Let's take, for example, 1 joule. And if you produce 1 joule burst of light in 1 femtosecond, you know, the peak intense, the peak power is in a femtosecond regime. And a femtosecond basically is the power of all the electrical network in the world, okay? So, but of course, this, you do that for only a femtosecond, okay? But nevertheless, that really gives you a sense of what we can produce with extremely short pulses and why sometimes we would like to get very, very short pulses instead of a steady long pulse. Next slide. So now you see, for instance, if you take this very high peak power that you have produced, as I say, 1 joule, 1 femtosecond, petawatt, and you focus this beam over a very small spot size, limited by the wavelength of light, of course, limited by the diffraction of light, then you are producing phenomenal pressures, okay? Pressure equivalent to something like 10 million Eiffel Tower on the tip of your fingers, you know. So this is very extreme pressure, of course, and it is the highest pressure that we can produce now, okay? So you can see already what we are going to do with this type of light, because we can really produce these extreme conditions. Next slide. So this is, I would say, not exactly a typical, but I mean, one of the lasers which is producing the highest power in the world. It's about petawatt lasers, you know. They are relatively compact, okay? Of course, you don't have to have petawatt laser, you have also terawatt lasers, you know, and so on. So, and, but this one is one of the petawatt laser, one of the most powerful lasers, and which are going to give us, you know, this incredible power. Now, next slide. Okay, next slide again. Next slide. Next slide, please. Yeah. Okay, now I'm going to talk about how can I get this extreme power, okay? We as I said, we start with a short pulse of light, okay? And a pulse of light comes out from what we call an oscillator, okay? And if we are taking this short pulse of light, with this at the beginning, and if we try to amplify the pulse with what we call an amplifying medium, there's a number of amplifying mediums that we can use, but if you try to amplify, trying to get more out of your pulse, then with a short pulse, what you are going to do, you are going to damage the amplifier. You are going to reach a ceiling very quickly because the pulse is short. So if you amplify it with relatively small amount of energy, you will reach, a very, very high intensity, and you will break down the material. Okay, and that is the problem. Okay, that was we were stopped by these problems for a long time. Okay, and then we came with the idea with Donna Strickland that before we were not going to amplify the short pulse directly, but before we will stretch the pulse. We will stretch the pulse. So when we started, we stretched the pulse by a factor 10, and then by a factor 100, after 1,000. Now we stretch the pulse by a factor millions. Okay. So what we do, we are reducing, of course, the intensity of the pulse accordingly. And then you can now amplify the long pulse. Okay. And we are using these grading systems, these diffraction grading systems, to really stretch the pulse. And we can do it so we can have, say, the red part of the pulse, going first, and the blue part of the pulse going last. And we can control that with the diffraction gradings. So when the pulse is stretched, then we can amplify it. And when it's being amplified, then we are going to do just the converse of what we have done. Okay, that means we are going to compress back the pulse, to this initial value. But this time, we are going to have a pulse with much, much more energy. Okay, 1 million times. Okay, more. And that was a trick. And of course, you have to do that very, very well, very carefully, because if you take femtosecond pulses, you stretch something like 1 million times, means you stretch it back to a nanosecond, okay? And then you are compressing it, amplified by 12 order of magnitude. And then you are going to compress it, 9 order of magnitude. So you have to do that very, very well if you want to have a very clean output pulse. Okay, next slide. And now with extreme light, you will see that we can produce, as I said, the largest peak power, the largest temperature in billions of degrees, okay? Much, much hotter than the sun, okay? The center of the sun. You can, as I said, you can produce the largest pressures. We can produce the largest acceleration. We'll be able to accelerate particles from 0 to the speed of light in a femtosecond, which means that you are producing phenomenal accelerations in 10 to the 25 G. Phenomenal, okay? So you see that you can do many things, and that's the reason why this field is so important now. Okay, next slide. Next slide again. Next slide, yeah. So now, you see, could you come back to the previous slide? Yes. Now, what I'm showing you is just atomic systems, okay? Where you have a nucleus, which is really composed of nucleons, protons, neutrons, and you have the electrons, you know, circling around this nucleus, okay? So until now, with the laser, you know, we were only, and with optics in general, what we do is only to to excite the electrons, okay? This is what we do when you shine a light, you know, on a wall, you are going to excite the electrons circling around a nucleus, okay, these kind of things. And because they circle around, they are going to re-emit the light that they get, and you are going to see the wall. Now you will see, and now with the laser, with a high intensity laser, then we are going to see that we can change things. Normally, you know, the electrons here, even with just common lasers, the electrons are not going to move by a large range, by big excursions. You know, it's a really relatively small amount of displacement. But with the laser, high intensity laser, now these electrons are going to move at the speed of light around the nucleus. And so they will move, you know, over very large excursions. Typically, the wavelength of light, okay, huge amount. And that's the reason why, next slide. Yeah, so now with the high intensity lasers, you see, we are going to move from the atomic, I will say, physics, where the laser was before the CPA, to now the subatomic regime, okay? So from the electron volt regime, this is the domain of optics, to the subatomic regime, which is giga electron volt or something, and so on. So we will now, instead of studying only the atomic systems, we are going now to start to study the nucleus systems, okay? And because we can produce this phenomenal displacement. So let me, next slide. Yeah, I'm going to now describe a few applications, okay? And this here, this is the history of over many years, you know, starting in 1960. I'm sorry, this was, we cannot see it. It's starting with, start with 10 Mayman, 1960, you see, and where the intensity of the laser he produced with his ruby laser was about 10 to the 8 watt per square centimeters. It was a lot at that time, but now, of course, it's nothing. And so the intensity increased, starting 10 to the 8 watt per square centimeter, gradually increase by using different techniques, and came up to about a ceiling which was about 10 to the 14 watt or so per square centimeters. And here you have this big plateau and we stayed about for 20 years on this plateau, and it was a 10 to the 14 watt per square centimeters. It was basically, this plateau was due to the breakdown, energy of most materials, at 10 to the 14, 10 to the 15, you are breaking down the materials, you are separating, the electron from the nucleus, and you are breaking down the material. So then that stopped at 10 to the 14 watt per square centimeters. So in 1985, this is where we came with Donna, with a chirp pulse amplification. Then we could circumvent these problems, and now we could really continue to climb up this curve. And so by increasing the power, we will really now going into different regimes, physical regimes. So I'm going to talk a little bit about these regimes. I would like just to, the one in purple here is a regime where we ionize materials. And one of our applications, for instance, I'm going to show, there's many applications, but one the most right now used is the micro machining, okay? Micro machining, you will see that we can really machine with exquisite precisions with femtosecond pulses. Now, if we increase, if we are increasing this intensity now to tend to be 18 or so watt per square centimeters, then what will happen is the quiver energy of the electrons, which oscillate around the nucleus, will reach velocity of light. Okay, and that was the first time the electrons, normal electrons, submitted to normal light, the electrons are very, very low velocity compared to the speed of light. Okay, but now we will be able really to reach electron will reach speed of light velocity. Okay, and that, of course. And so what happened is the mass of the electrons, of course, is going to change, okay? And so everything will change in optics, okay? Now, optics in these regimes, is completely different. And we call it relativistic optics now, okay? Because the electrons now around the nucleus will become relativistic. Now you have, if you go up in a yellow band, then not only the electrons, but the much more massive protons, will be able to be accelerated, okay, and to the speed of light. So we will be able to make relatively easily, relativistic protons, for instance. And when you go even higher, 10 to the 20, above 25 to 10 to 29, in fact, what you are going to get is you will be, the field of the laser is so large, okay, that you will break down the vacuum, okay? You will break down vacuum in its components, electrons, positrons. So you are going to generate, you start with light and you will produce matter. So you will materialize light, okay? Which of course is something, it's one of our dreams, to do. Is we are not quite there yet, but yet, I'm sorry. but we are very close, okay? So, so that gives you a little bit some idea, but of course there's really many other applications, but just give you an idea of what you can do with light now. You know, you can create matter with light, okay? Okay, next slide. Next slide. Next, yeah. Okay, I'm starting now with the micro machining. Okay, as I said, the one at the bottom. So, if you have pulses not so short, say beyond, 10 minus 9, a nanosecond pulse, 10 minus 9 seconds, you know, which is very long for us. Okay, because we are working in a femtosecond, a million times faster. Well, if you are using nanosecond pulses to do some machining, you know, you can do it, of course, and people are really doing it, okay? But what happened is the fact that when you send the pulse on your target, you know, in order really to machine the material, then the pulse is long, is a little bit long, so the temperature is going to really to be to diffuse, you know, around, spread around the spot size, and so you are going to elevate the temperature a lot around the spot size. So you are going to basically make a big crater. Okay, a crater much larger than the spot size itself. Okay, now if you are using, because the pulse is long, because the pulse for a nanosecond, the temperature has a time to propagate, the heat has time to propagate. Now, if you have a short pulse in a femtosecond time scale, so a pulse which is 1,000,000 times faster, then what happens is, of course, you are going to hit your target, but this, you are going to raise the temperature of the area you're hitting with the laser, but nothing, you are going, the temperature doesn't have a time to spread out, okay? So you will remove just a relatively small amount of of material. So you will be able really to do an extremely clean job, very accurate. Okay, let me show you. Next slide. Yeah, for instance, if you are using, you see, femtosecond pulses, you can really do all this exquisite, you see all these holes that you can really punch, you know, and look, they are all the same. They're all the same. And the diameters is 1/3 of a micrometer. You see, look at how sharp are these holes. Very, very sharp, okay? So this is really really the best way to do machining, really, okay? Now, next slide. And now what, of course, if you want really to do exquisite machining, of course, as an application, you think about ophthalmology. Because in ophthalmology, what you like really to do, of course, is to do very, very, what you need to have is really a very accurate scalpel, right? And so you can cut things very, very cleanly, okay? And let me show you, next slide. Yeah, for instance, if you want, you know, this I show, for instance, a retina, okay? And the retina, you know, is about 500 micrometers in thickness. So what you can do, you can really send the lasers, focus it in within the retina, and make, so each pulse is going to make a bubble, okay? A very teeny tiny bubble. And if you move the laser around, you can in fact cut, the material in what we call flap. You can make flap, very, very exquisite flap. Okay, next slide. Yeah, for instance, that is the kind of flap you can really produce on a cornea, or here, of course, on the cornea of the pig. But now, we have this procedure has been done, and it's a very huge success because more than 2 million patients a year have this procedure now, just to correct for the visions, or for if you have cataract, if you have problems with the cornea and so on, of cataract and so on. You have 24 million eyes a year now. No, it's 2 million eyes a year, and 24 million since we came up with the applications. Yeah. Okay, so these are gorgeous applications. Okay. Next slide. Yeah, and also you can do things like transcorneal transplant, and so you can do that because you have, instead to have like a mechanical trifine where you're punching, you're using a razor blade, basically, you are using now the laser, and you can have much larger flexibility. Okay, next slide. Okay, now I think I'm going to the green area. The green area, I told you, is where the electrons can be relativistic. Okay, they are accelerated by the laser. The field of the laser is so large, then the electrons now are moving, at the speed of light. And that's the reason, again, we call that relativistic optics. Okay, and now next slide. And what we are going to do now, we are going to try to accelerate particles, okay? And you will see that we can accelerate particles in a very compact manner to very, very high velocity. I mean, the speed of light, of course, but I mean, with a very large Lorentz factor. So, and what I'm going to describe here is a technique which is being used, which was proposed by Tajima and Dawson in 1979, where now what we are going to do is next slide, I'm going to show you. Sorry. Next slide. Yes, thank you. What I'm going to do now, I'm talking about electron accelerations. I'm going to use a focus the laser in this gas jet, noble gas jet, okay? And, like a millimeter in size. And what we are going to do, we are going to focus the laser in this gas jet. Doing that, we are going to really produce a plasma of electrons and protons, basically. This kind of a soup of electrons and protons. And you are going to produce a plasma, and the electrons are going to drop into the trough of the plasma wave here, and are going to be accelerated because they are trapped. And the plasma wave is produced by this laser, this very short pulse, right? Because remember that the pulse is in femtoseconds, okay? So the size, I mean, the size of the pulse is in micrometers, okay? Just speed of light, okay? A femtosecond at the speed of light, you will get micrometers, okay? So you have this this wave of space in micrometer scale. And they will be dragged at the speed of light. And what is phenomenal is we have shown that now we can accelerate particles to energy of giga electron volt. Giga electron volt per centimeter. Now you say, okay, you maybe don't understand this, but giga electron volt per centimeter is enormous. If you consider that with a conventional technology, next slide, yes. If you want, I'm sorry, I don't understand that. Yeah, if you want really to accelerate particles now with conventional technology, it will take you, a giga electron volt will take you, people like this, 300s of more, like accelerator of 300 meter diameters. So huge compared to single centimeters, okay? So that you understand. Next slide. Yeah, one thing also, I'm talking about accelerator because accelerators is very important for the society, okay? Not only for science, but for society is very important because you can produce many things, okay? And I will show you that some of the applications, particularly in medicines, nuclear medicines and so on. So next slide. Next slide. Yeah. So now I'm going to talk about some of the applications, so I'm going to talk about low-hanging fruit. The fact that we can accelerate particles to very high energy. I'm going to show you now some of the applications, in a medical field, but also in the environment. For instance, one of the applications right now will be maybe to get rid of the nuclear waste, okay, and so on. So next slide. Next slide. Yeah, we go to next slide. Next slide. Please, next slide. Yeah, thank you. So now we can just going a little bit fast here, but we can accelerate electrons. We can also accelerate protons, okay, and to very high energy. I showed you that if you want to do that, if you, for example, want to accelerate protons with close to GeV energy, it will take you humongously big machines like this one, which is almost a kilometer, to accelerate proton to the speed of light. Okay, and of course, this is a very costly machine, and we can do that with the laser over millimeters. Okay. Next slide. Yeah. Some of the applications, for instance, why do you want really to produce protons, accelerate proton, for instance, to fraction of GeV, so speed of light, close to the speed of light? Because you have fabulous applications, and one application is, for instance, proton therapy. Okay, proton therapy is much better than X-ray therapy or electron therapy. Okay, if you have a tumor, for instance, The problem with X-ray therapy and electron therapy is if you are going to burn the tissues which are before the tumors. So when you want